Good morning, everybody. This is Mr. Steele. I'm not here with you, obviously. Well, unless you think I'm a disembodied voice, in which case, yeah, I'm sort of here with you. I'm here with you in spirit, because, in fact, I'm at Challenge Day, which I'm very excited about. But unfortunately, that means I can't be in Calculus 2. If I were able to be in 2 places at once, well, then I could probably be in 3 places at once. I'd just do that instead of teaching with 1 of me and 40 of you. So, there you go. So, of course, the problem with me not being here is that we can't do the lesson, so we're doing it this way. So, you're going to be taught by a disembodied voice today. Hopefully you enjoy it. So, if you haven't already, if you could pull out your notebook. Well, you probably already did that. You were probably instructed that already. But anyway, if you could get down the essential question and everything, it's going to be up here for a while. So you can write it down while I go through a short little demonstration we're going to use to start today's lesson about exponential derivatives with. And once you finish that, we'll be moving on forward. We've got a couple examples today. I want to say it's like 3 or 4 examples across the 2 different topics that we're covering. And then there will be 2 try-its at the end you'll have time to work on and then check the answers with on here. And then the rest of the time you can work on homework. So hopefully it'll be a pretty decently paced lesson, give you an opportunity to see some some examples and applications with exponential derivatives in a few different contexts, and you'll be good to go from there. So, where we're going, I mean, obviously our goal today, just right off the bat, even if you're reading the thing, we've got 2 goals. Our primary goal to start things off is we want to find the derivative of e to the x. And why e? Well, there's a lot of reasons why we choose e. E is kind of a special number, 2.718281828. But of course, we just looked at ln of x back on Tuesday, so e is the inverse of ln of x, so it's a natural place for us to go. Natural place like a natural log. That's a math joke. Write that one down. So what are we going to do with first? I'm going to go through, and I'm going to use the graphing calculator to do something kind of interesting. You might think this is really a non-intelligent thing to do. What I'm going to do is, since we don't have any intuition about the function e to the x, I'm going to graph the function, and then I'm going to graph its derivative. So you don't need to do this on your calculator now. This isn't a useful thing. I wouldn't recommend you doing it. Not the least of which because your calculator battery hates it when you do it. It totally eats it up. But basically, the first one just says e to the x. The second one says calculate the derivative of e to the x with x as the variable and evaluate it at the value x, which then, of course, will change and vary based on as the independent variable on our graph. So to start with, we know a little bit more about e to the x than we do its derivative. Basically, it's infinitely more because we know nothing about its derivative. But if I graph it, we get that nice normal exponential graph. There it is. So it hugs this little asymptote here, the horizontal asymptote at y equals 0, and then it goes up pretty quickly. So there is e to the x. So I want you to stare at it, get it in your mind's eye for a second, because next I'm going to let the calculator graph its derivative only. So I'm going to go back, I'm going to select the derivative of e to the x. So the calculator is going to calculate the derivative at a whole bunch of places and graph it down. Let's see what it looks like. Okay, ready? Wait. Whoa, timeout. You can't see it, but I'm making that little timeout sign here. I thought I what? I graphed the derivative. It looked like this. I graphed the original function. It looks like this. Those 2 guys look pretty darn close to one another. Like they look like basically the same graph. Like almost identical. I mean, let's trace a point here. Like, I don't know, it's going to take a second. You can't see my finger, but you can see my mouse. Hopefully it's kind of small, but try it here. So let's trace a point. There's a point right there. So it looks like, I don't know, the point at 1, the value of the function is 2.71828. Oh, that's interesting. 2.71828. And then if we go back to the original function and plug in 1, take a look at this. It's pretty weird. We get the value at 1, 2.71828. So it seems like these 2 graphs are really similar to one another. So something you might think, just from looking at these pictures, is that the 2 graphs, or the 2 functions, the derivative and the original function, are related to one another in a pretty direct way. Like they must be very similar to one another. Well, the fact is, we can actually prove and find what the derivative formula is if we use that technique we learned yesterday, log differentiation. So let's look at the function for a second. Before we get to what that is equal to, like let's save that for just a moment. Let's look at the function y equals e to the x, and let's take the derivative of it. Or sorry, let's take the natural log of it. Pardon me, I'm kind of tired right now. So we're going to take the natural log on both sides. Remember, the reason we did this was it allowed us to simplify problems and actually evaluate the derivatives that we might not otherwise be able to do, or more likely we wouldn't be able to do easily. So over here, ln of y equals ln of e dx. I just took the natural log of both sides. So from here, is there anything that we can do? Oh, yeah, I can't call in anybody because I can't see you. You're not here. You're in the future. So yeah, unfortunately that's not going to help. What I can do though is I can go ahead and take this little x and bring it down in front. We can use one of those log properties. In fact, it was the first one we looked at back on Tuesday when we started this unit. So we get x times the ln of e. So ln of e, well, let's think about that for a second. What power of e gives us e? Well, that's obviously equal to 1. Natural log of e is 1, meaning that ln of y equals x. So, okay, from here, nothing we can simplify. But remember, our goal is to find the derivative. So if we want to find y prime, we're going to have to differentiate this whole guy. So the derivative of ln of y, it's going to be a chain rule thing. It's implicit differentiation at its finest. Derivative of ln of y is 1 over y times y prime. You might also go with the alternate form y prime over y. Derivative of x, everybody, 1! Good job, everybody. 1 it is. So we get 1 over y equals y prime. Of course, our goal is to get y prime. So y prime is equal to, multiplying both sides by y prime is equal to y. Well, that's interesting. This says the derivative is equal to the original function. Well, that original function, back in the day, goes right in there. So it says that y prime equals e to the x. So as bizarre as this sounds, what we've taken out of this little excursion is that the derivative of e to the x is equal to none other than e to the x. Like, this is a fact. This is something we're going to be able to use a lot going forward. So what's awesome about this? E to the x is its own derivative. Like, it is efficient. Not that, that's something that you necessarily want to aspire to. Little kids don't grow up saying, I want to be my own derivative when I grow up. No, that's dumb. That doesn't make any sense. But in fact here, it's pretty cool. Like, if you forget what the derivative of e to the x is, well, it's staring you right in the face. It's the exact same thing as the original function. So that's pretty cool. Now, of course, we've got this, but of course we want to look at, what happens if something more interesting is happening in the function. What if we're multiplying by something else? So of course it doesn't quite end there. Like, just because the derivative of e to the x is e to the x doesn't mean that's the end of our work. Instead, we might look at the fact that derivative of e to the f of x. So if we have a problem where there's some function composition happening, in this case we plug in something f of x, it could be x squared, it could be sine of x, it could be something horribly, horribly worse. Just depends. That's going to be equal to, if we treat this, we start with the function rule itself. So derivative of e to the u is equal to e to the u. So in this case we'll get e to the f of x. And then times the derivative of the inside, which in this case would be f prime of x. So the chain rule version, or the more general version of the derivative of e to a power, is e to the f of x times f prime of x, or f prime of x times e to the f of x. Just depends on what you're looking at. So in a sense, what we've just come up with is we've been able to derive using log differentiation in one case, and then just kind of using the chain rule really quickly and implicitly, we were able to find the derivative rule for e to the x. So e to the x is pretty darn special. Its derivative is itself, or even when it's not just e to the x, when it's e to the f of x, itself shows up again in the actual derivative. So kind of cool. So with that said, we want to be able to use e to the x in all the normal contexts that we would any other kind of function, like ln or power functions, any of those things. So let's take a look at a couple problems that use this rule. It's not a difficult rule to get used to. It's just a little weird when you start that it's kind of repetitive. So let's look at that. Alrighty, so let's take a look at an example, as I just said. And if you're wondering why I'm repeating myself, if I happen to do that, it's because I have to pause it in between and let the video compile itself. This isn't a very quick process. So let's start with something pretty simple. Let's just find a derivative. So let's find f prime of x for the function. Let's go f of x equals, how about e to the x cubed? So it's kind of parallel to the first ln natural log derivative we did on Tuesday. So f of x equals e to the x cubed. So where I'm going to go here is for those people that kind of get that don't like that definition at the bottom here, that have trouble with this kind of faux chain rule that I just did. Let's just go through and use the chain rule in its most explicit form here. So let's start with fu. See, sometimes I can't stop myself. So fu. So what would be the outside function right here? Well, of course, we can kind of see it right now. We've got this little x cubed kind of squeezed inside the e to the x. So I would say that our outside function is e to the u. That means u is equal to x cubed. So straightforward, this is the same way we did it back in the day. We've just got different functions here that we're playing with some cool new rules. Okay, well, second, f prime of u is just the derivative of e to the u. That's just equal to e to the u. Derivative of e to the x is just e to the x. So e to the u's derivative is e to the u. But of course, we know u is actually something interesting. So what is u prime, everybody? 3x squared. It is 3x squared. Good job. So of course, we've got u prime. So now our final derivative, f prime of x. We know that the chain rule says it's f prime of u times u prime. So plug everything back in. We'll get e to the u times u prime. But of course, that's not what u is. U is really equal to x cubed. So we'll just make our substitution. We'll say that e to the u is e to the x cubed. And of course, that's times u prime. I just like to put it in the front because I like shoving e at the end of the whole situation. So from working on it or looking at it, we get that the derivative is equal to 3x squared e to the x cubed, or you can reverse it, e to the x cubed times 3x squared. Either way, we get the same thing. So notice it works just fine with the chain rule. If we'd used it the other way, if we'd just done this e to the f of x times f prime, of course f of x was equal to x cubed, and f prime then would be equal to 3x squared. So e to the x cubed times 3x squared. It works out totally fine, just the same, no difference. So same way it gets us there. So if you're not comfortable with that kind of shortcut version of the rule right off the bat, that's okay. Just work on using the original chain rule and it'll work out fine. You don't have that many problems you'll have to work through, and eventually you'll get comfortable with it. So any questions? Too bad, made you try. Can't answer any of those questions. So second, now that we've got one little example kind of thrown in there just with taking the derivative, let's look at something a little bit more involved. So how about, let's say, how about we go through and find and classify some relative extrema. So normally, if I was a good video editor, I would cut out me writing out the stuff, but then you guys wouldn't have any time to write it down. So really, this is thoughtful and considerate of me. So in other words, you're welcome. So almost there. I'm just trying to make sure that our example has some cool stuff going on. And by cool stuff, I mean cool stuff in my opinion, probably not in your opinion. Of course, it goes without saying. So here is the problem we are going to set to work on. We want to find and classify any relative extrema, all the relative extrema even, of f of x equals x squared e to the x minus 8 e to the x. So first thing I want you to do is just take a look at that function for a second and see, are there any special rules we might need to use? So in particular, last term we had stuff like implicit differentiation. Obviously that's not going to come up here because there's no y. But then there were also product quotient and chain rule. So you've always got to be on the lookout for those guys until they become all but automatic. So looking at this guy, do you see anything that requires a rule? Oh, yeah, I do. I see one. I can't speak for you guys, but I see right there that we're going to need a rule. What rule would that be? Well, x squared times e to the x says that we need a little bit of product rule action in here. So we need to use the product rule. So we'll take care of that guy as we start off. So we're looking at some product rule. The other guy, yeah, it is two things being multiplied, but of course 8 is just a scalar, so it's just the scalar multiple rule. So from here, first thing we need to do is if we want to talk about relative extrema, we need to find the derivative so we can set it equal to 0 or see if there's anywhere it's undefined. So f prime of x. f prime of x. Well, first thing we'll do is we'll do the product rule part. In fact, you know what? Just for clarity, I'm even going to change the color here. Pretty colors. Let's go with f prime of x. So what I'm going to do is I'm going to do the normal stuff in blue, and I'll do the product rule piece in red, just first so it really stands out visually. So product rule, f prime g plus g prime f. So we'll have to do the derivative of x squared. Now I know you can probably do that in your head. It's okay, I'm just doing this for clarity's sake since I'm not here to answer questions. Plus, we'll have x squared times e to the x derivative, and then that whole thing will subtract away the derivative of minus 8 e to the x. So of course the derivative of negative 8 e to the x is scalar multiple times the derivative of e to the x, which is e to the x. So there we go. We've got everything ready to go. We've actually found the derivative on one part. We just need to go back through and look at the first part and simplify everything. So as I look at this guy, what's the derivative of x squared? 2x. It is 2x, good. E to the x is just e to the x. On the second one, we get x squared again. The derivative of e to the x is still e to the x, weird as that is. And then of course we're still subtracting off e to the x. So this guy is actually equal to our derivative. We just found it. We just had to use the product rule a little bit. It wasn't hard. We just had a regular e to the x, no chain rule, nothing else fancy. But something you might notice here is that all three of these terms, as weird as it is, and it might not seem necessary or useful to you, but it actually is, there's actually a GCF here. So let's pull out the GCF in this case and see what we're left with for f prime. So what's my GCF? Can I pull out an x? No. I can't pull out an e to the x though. So just pull that out. All we're left with then is 2x, x squared, and minus 8. So if we put those guys in descending order, we'll get x squared plus 2x minus 8 is equal to my derivative. So I've found my simplified version of f prime. So awesome, great. That's a wonderful thing. But of course that doesn't do much for us. We've done like 1/4 of the problem. So what we need to do next is find the critical numbers. Like we need to know, where does this derivative equal 0 or undefined? Well, the first thing that I can see is that there's nowhere that this guy's going to be undefined. The reason is both of these two guys are nice and continuous. E to the x is a little bit funky. You're not super familiar with it, maybe as much as some of the other ones, but it just looks like that. Goes continuous from both sides. There's domain is all real numbers. We're good to go there. And same thing with this polynomial. So in other words, like this is going to exist everywhere. The only thing we can look for is there anywhere where it's equal to 0? So our question to ask ourselves, if we want critical numbers, is when does e to the x times x squared plus 2x minus 8, in this case our derivative, when does that puppy equal 0? So when does that happen? Well, there are two possibilities. We could have e to the x equals 0, like that's one possibility, and the other guy is we could have that polynomial equal to 0. And I'll trust that you believe me when I say that that factors into x plus 4x minus 2, and of course where does that guy equal 0? Those would give us our other critical numbers. Well, over here it's easy to find our critical numbers. Negative 4 and 2, positive 2. On this side though, the question is, well, when does e to the x equal 0? Like, is there any time we could find that out? Like, what would that x value be? Well, again, another thing that might not jump out of you, because, you know, ln's and stuff, you don't do that all that often when you're not doing calculus. But if I want to solve for x, I could take the ln of both sides. So ln of e to the x, of course we know that brings down the power, equals ln of 0. So ln of e is equal to 1. We already saw that earlier. So x is equal to ln of 0. Yeah, there is no ln of 0. That doesn't work. So in fact, there is no critical number that comes from the first part. And in fact, something that we'll always see, just that we can even visualize when we think about the graph of e to the x, is that e to the x is always going to be, that was annoying. E to the x is always going to be positive. So in fact, this guy will never give us a critical number because e to any power is always a positive number. So in fact, these are our only critical numbers over here, negative 4 and 2. So kind of awkward, kind of interesting, but that property of e to the x, e to anything always being positive, huge help in our process, because then we don't even have to play around. We don't even have to think about the ln of 0 and possibly confuse ourselves or forget something. So there are two critical numbers. What that means is I can make up my table. So if I were a genie or a magician, I would have already done it. I'm not a genie or magician. Sorry to burst your bubble. I can't grant you 3 wishes. Oh, don't you hate that when you try to make a straight line and fail miserably, and then the straight line attaches itself to something else? Yeah. Horrible thing for me. Okay, let's do it this way. Cheating on my straight lines. There we go. Okay, so we're making our table. We're going to look at the derivatives values, so checking the slope, what's the pattern, increasing, decreasing, decreasing, increasing, etc., etc. So the two places where I need to have zeros here, I know this is a gigantic table, it's just, you know, bad spacing on my part. I have a lot of room to work with here. I'm going to have values at negative 4 and 2. I know that the value is equal to 0 at those points, because of course if you set that equal to 0, the whole derivative is equal to 0. So then I've got to see what's the slope like from negative infinity to negative 4. from -4 to 2, and from 2 to infinity. So let's think about this a little bit. So looking back at our original derivative, which is of course right here. Here's our derivative right there. So as we picture this guy, I find it probably easier to use the factored version. Like my f prime is equal to e to the x times x plus 4, x minus 2. And I want to think about, well, what sign would that be for various numbers here? And I'm going to choose -5, 0, and 3. And I'll add the parenthesis there that somehow I forgot. Okay, so looking down here, looking at the signs. At -5, e to the x is always positive. Then we're going to have negative, negative. So positive times 2 negatives is positive. In the middle, if I plug in 0, I get a positive. I get a positive and a negative. So 2 positives times the negative is negative. And following the same strategy, we're going to get 3 positives over here. So we get plus. So in fact, we have 2 relative extrema for this particular function. At -4, we're going from increasing to decreasing. And at +2, we're going from decreasing to increasing. So to formally write out our answer here, we have a relative maximum at x equals -4. And the reason for that is the function changes from increasing to decreasing, or f prime, the derivative, changes from positive to negative by the first derivative test. And then second, we have a relative minimum at x equals 2 for the opposite reason, because f prime goes from negative to positive. So in fact, we found both relative extrema, and hopefully, if I go check on the calculator, he'll confirm the same exact thing for me and say that the same answer is true. So let's find out. Oh, mighty calculator. Yes, master. Could you graph this function for me? Right away, master. Please say no to Siri. I do not like her. That's okay, calculator. You'll always be my favorite. So let's see. We've got e to, that was not correct. So we got x squared times e to the x minus 8 e to the x. And now what we're hoping that we see here, looking at this function, will be something that's increasing up to -4, then decreasing, and then increasing again at +2 and onward. So let's find out. We've got our window to standard. Let's see what happens. Okay, so obviously our window not doing quite so well. Let's minimize this a little bit. Let's make our y min, I don't know, -30. No, why would I do that? You know better. -42. Let's look at that guy. Let's go 5s. See if maybe this helps. It might not help at all. I might be completely off here. There we go. Okay, so let's see. Does this match what we have? So first thing is it's supposed to be positive over here. I don't see enough of the picture to be able to tell what's happening there. But you can imagine maybe there's some sort of maximum there. I'm not sure. Like, we'll have to zoom in a little bit further. But it's definitely negative down here and positive up here. So at least at that point we're okay. So let's zoom in on this half. Over on this left side, let's see what's happening over there. So let's go -2. That's not what I meant. Bad me. Let's go y min. Let's go from -2 to 2. And then let's go from -10 to 0 and see what this looks like. See if we get any sort of picture. Okay, so notice that's kind of interesting. We're up above the thing. There we go. This actually matches. It's really, really steady and not very steep. But notice that the function is getting bigger up here, and then it starts to go down again. So basically, although our picture isn't perfect, if I ignore all possible like picture sizes, we get something that looks a little bit like this, and then that going up. Like that is our function, f prime, or f of x in this case. So in fact, it does match what our derivative was. We just had to be kind of cutesy with the calculator to make it show up a little bit. So kind of interesting. Either way, the most important thing, take the derivative, set it equal to 0, understand that e to the x is always a positive thing, so it won't affect our critical numbers, and then we can find our relative maximum and even justify it, although I just did that verbally here. So there we go. E to the x, pretty straightforward, not the hardest thing to work with, but definitely something that has its own little twists and twists, not twists, like e to the x doesn't go out with its lover anywhere. So twists. So there we go. Let's move on. Okay, so we've got all that stuff about e to the x. Of course, the question in the back of your head is probably when does this get over? But the other question in the back of your head in the math happy section that I'm slowly tapping into one day at a time That question is, okay, fine. We know how to find the derivative of e to the x now. Ooh, big deal. E is just one single number. There are lots of other functions and lots of other exponentials with lots of other different bases. So like, what's the derivative of 2 to the x? What's the derivative of 15 to the x? What's the derivative of 42 to the x? Because of course we can do x to the 42nd, that's 42x to the 41st. We can do x squared, that's 2x. We can do x cubed, that's 3x squared. What about 3 to the x? So of course our next question is, what is the derivative of b to the x? So we want to figure out what is the rule for b to the x. Now of course with that said, like b to the x, for whatever reason in calculus, e to the x is the more common function. Probably because it's such a clean thing, you get such a pretty answer. I mean, the derivative of e to the x is e to the x. But of course b to the x is something we might be interested in as well. Like we graphed 2 to the x from the beginning of Algebra 2, back when we did logs. So it's something definitely worth considering. So what we're going to do is, once again, I'm going to derive the formula for b to the x along the same idea of what I did back here, except I'm going to do it in a slightly different way. Because basically our strategy here, or the way we're going to kind of see where this derivative comes from, and that I often use to help myself memorize or figure out what the derivative is, comes from writing b in a very specific way. So what I'm going to start with is I'm going to start with the fact that b is really equal to e to some power. Now you could say, well, what the heck is b anyway? Well, that's beside the point. The reality is b is the same thing as e to the ln of b power. So now there's a couple reasons that this is true. One of the reasons that this works out is, of course, that e and ln are inverse operations. And when you take an or a function of its inverse, like, they cancel out to just whatever the argument is. In this case, that would leave us with b. So that's one way to kind of visualize that it's true. There's other reasons that allow us to visualize that it's true. The one that I think is most powerful is to just let the calculator kind of verify this for us. So let's say, for example, that we want to figure out e to the ln of 4 power. Like, according to this, e to the ln of 4 would just be equal to 4. Well, let's see if the calculator supports that, just so we get some, concrete visualization of what we have here. So e to the ln of 4, 4. Let's try e to the ln of something really more valuable, 42. We could try e to the ln of 16.7. We get 16.7. So notice that the calculator is showing us that same thing. These two guys are really inverse operations. So hopefully, although it's not a perfect explanation, and I don't really want to take the log of both sides, natural log of both sides, and show that they come out equal, in reality, what we're seeing is that this actually works out. So from here, b is equal to e to the ln of b power. So now the reason that we want to start there is because that means that, I love cloning, b equals to ln of b. If that's true, that means that b to the x is equal to e to the ln of b to the x. So again, all I'm doing is taking both sides to the x power. Doesn't matter what x is, I can do that. They're both the same thing. So now looking at it, on the left side, we obviously get that thing that we're interested in at this point. We want to talk about the derivative of b to the x, so we need to be able to look at it. We need to have it as part of what we're looking at. E to the ln of b to the x, though, is really just a simple exponent rule. Like, think back in your mind, x cubed to the 7th power. Well, of course, we go, well, that's x cubed 7 times, so 3, 6, 9, 12, 15, 18, 21. Of course, we just multiply the exponents, and we get x to the 21st power. So the same thing is true here. On the right side, e to the ln of b to the x, we multiply those two exponents together, and we get e to the ln of b times x. And of course, ln of b is just some number. Like on the calculator that we were playing with a few minutes ago, ln of b, it could have been something like ln of 4, which is equal to 1.38. Could have been ln of 42, which is 3.737. It's just some constant, or in this case, some scalar, some value that we don't really care to worry about the value of right now. It's just something. So now the question is, well, why would we do that? Like, why is that valuable? And more importantly, how is that going to get us the derivative? Since I said we were going to find the derivative here. So how do we do that? Well, if we look at this guy now, we really just have a chain rule problem now. So it might not jump out at you right away, but we're trying to find the derivative of this guy on this side. So looking at it for a second, we can fu. It's going to be equal to e to the u, and then what would u be? Well, if you look at it, it's just going to be the power. It's ln of b times x. It's some number, some funky number that's not very pretty, times x. Well, okay, f prime of u is e to the u prime is just ln of b, because any scalar times x, the derivative is equal to the scalar. ln of b, it's just the slope of this random linear function with a bizarre transcendental slope. So of course that means that our derivative here is going to be equal to e to the u. Sorry, I should always write this out correctly. So f prime of x is equal to e to the u times the ln of b. But of course u, it says right up here, is ln of b times x. So that means this whole function is bringing that constant out to the front, ln of b times e to the ln of b times x. And of course the only thing left here is, of course, e to the ln of b is really ugly, but we just said right up here, it wasn't that long ago, b is equal to e to the ln of b. Those guys are inverses. So in fact, those two guys would cancel. It's almost like we undo the work we did here, and we get that the ln of b times b to the x is equal to our derivative. So what is d dx of b to the x? Well, that's going to be equal to the ln of b times b to the x. And the nice thing about this rule is, well, there's two nice things about this rule. The first one is that I'm not going to ask you to do a whole lot with it going forward, because the AP test won't either, and honestly we don't worry about the rate of change of this function all that often, or at least not in situations where we wouldn't have a calculator. The other nice thing though about this function is that it actually works for any b, as long as b is of course a positive number. And one of those numbers that works is actually e. Like, look at this for a second. If we take the derivative of e to the x using this formula, ln of b, well, b is going to be e times e to the x. What's ln of e? It's just 1. So it's equal to e to the x. So really, the derivative e to the x is really just a special case of this random derivative, ln of b times b to the x. So for any base, any positive base, power, it works out. So now, with that said, last year, when I introduced the concept this way, which seemed pretty cool to me, it wasn't the way I learned it, I just kind of memorized it, but at the same time when I introduced it, my class collectively pretty much tried to, well, they tried to like overthrow me. Like they weren't happy with this explanation. They didn't like it. For whatever reason, they just weren't as comfortable with that concept, like the idea of the inverse operations there, which I understand completely. So if that just felt like gibberish to you, blah, 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 if that was a simulation of what you just listened to, that's cool. There's another way that we could actually do the same thing. And maybe this way is better, maybe this is the way you want to stick with it. This would be a good way that appeals if you liked the log differentiation yesterday. So what do we do here? Well, let's do the same thing we did when we derived the expression for the derivative of e to the x. Take the natural log of both sides. So of course on the left side, ln of y is just ln of y for the moment we haven't differentiated yet. On this side we bring down the x times the ln of b. Okay, well let's differentiate. So d dx in this case. On the left side we get 1 over y times y prime. That's our natural log rule. On the left side, this is just ln of b times x. This is the exact same thing that we dealt with over here in u prime. That's going to be equal to just plain old ln of b. If you stare at it for a second, I bet you can see the next thing coming. From here, we multiply both sides by y. We get y prime equals the natural log of b times y. And what is y, everybody? b to the x. So in other words, if we make our substitution back substitute, we get y prime equals the ln of b times b to the x. So it gives us the exact same expression that we got on the left side. It just used a different strategy to get there. So to me, it doesn't matter which one you use. The one on the left is probably the cleanest one. It's the coolest one. It kind of explains why back in the day, Algebra 2 textbooks started to get a lot of e to the ln kind of stuff where you'd have to use inverse operations for it. The right side uses log differentiation. It's a little bit slower and clunkier and harder to use in the context of product rule type problems, but both of them work equally well if you're careful. So I don't care which way you do it. Really, in all likelihood, I'm going to ask you like a question or two on the test about this topic, like probably even a multiple choice question instead of anything else. So really, if you just want to memorize this, of course, option 3 is always available to you. So just to throw that in there so you make sure you got it. You could also memorize. Commit it to memory. Tattoo it on the back of the eyelids. I don't know, whatever you guys do nowadays. So there we go. We've got the derivative of b to the x. So I don't want to spend forever on this part because it's the least important thing that we actually have to do. But you do want to see at least one example of this guy in action. So let's take a look at one. So we're approaching the end of the actual lecture portion of today's lesson. So almost there, guys. We've almost made it. Alrighty, so like I said, let's take a look at an example here. Let's see some of this stuff in action, at least as far as like the tougher kinds of questions that I might ask you, or more realistically, the realistically tough questions I might ask you. So let's use this one. Sorry, I broke my own rule about writing out the directions ahead of time. Basically, what I want us to do is I want us to just take the derivative here and look at both methods and see which one. Let you have an opportunity to see both of them in full action as opposed to a derivation, and see which one you prefer to use when you go forward and do this yourself. So we're going to use it in this case. We're going to apply this guy, and we're going to find the slope of the tangent line to the function 4 to the square root of x plus 1 at the x value 3. So we're going to see what the slope is at that point. We don't need to find the entire tangent line. Of course, we know how to do that. We're just not going to do it right now. So what are we going to do? Well, as I said before, we've really got two options here. We could go through, just like I did in the derivation, and we could use the fact that this is really e to the ln of 4 times something power, or we could use log differentiation. So I'm not sure which one you guys want. I could ask you to vote, and then I could just like not do anything about it. It'd be like a coup in another country or something. But in fact, let's just do it this way instead. Let's just do it both ways really fast. Or let's start it out and see which one we like better. So let's start on the left side. Let's go with the same method we used on the left over here, rewriting it as e to the ln. So that we can make it something that has e to an f of x power. So in this case, our key element here is we need to figure out a way to rewrite 4 to the square root of x plus 1. So the way I'm going to do that is I'm going to write it as e to the ln of 4 power, and then of course that's all to the power square root of x plus 1, so that means we're going to end up multiplying the exponents because of that old exponent rule that we had. So in this case now, our exponent is ln of 4 times the square root of x plus 1. So now when we take the derivative, of course, we can use the chain rule. So we don't have to go through and use u and u prime, like although I will for simplicity here. Start with fu. Fu is e to the u, because we're going to let u equal the ln of 4 times the square root of x plus 1. And again, keep in mind the ln of 4 is just a constant. It's just some scalar. It's a number. It's a little bit bigger than 3 or 1. I think it was like 1.387. So of course, f prime of u, derivative of e to the u, is e to the u. U prime is messy. This is messy. But ln of 4 is a constant, or a scalar. And then the derivative of square root is 1 over 2 square root. So this will be times 1 over 2 square root of x plus 1. That all simplifies to ln of 4 over 2 square root of x plus 1. And that means that my entire derivative, my f prime of x, or in this case it'd just be y prime, but whatever, we're going with this guy, is going to be e to the u times that whole mess. You know what, I'm just going to save myself the trouble. U is ln of 4 square root of x plus 1 times the derivative of u prime, which is ln of 4 over 2 square root of x plus 1. So at this point, although it's not pretty, it's not fully simplified, I could go one step further and just simplify that part, the e to the ln of 4. It's going to end up being this gigantic mess at the front, all times 4 to the square root of x plus 1. So right there is our derivative. Now it's not our answer, we're supposed to find the slope, but for the moment we found the derivative. And all we're doing here is we're trying to give you an opportunity to see which method you might prefer. Okay, so what I'm guessing right about now is you probably don't want to do this method. It looks horrible. I understand, totally cool. So let's look at the other method for a second. Let's take a look at log differentiation. So what was this? This would be what I'd call the inverse ops method. So this was the favorite of exactly -17 of the 43 students in my third period term calculus class last year. So take that for what it is. Okay, so on this guy, I said let's use log differentiation. I think this is a lot cleaner. I always want to go the other way, but I think it's cleaner this way. So what do? We take the natural log on both sides. That's going to allow us to have ln of y equals to the square root of x plus 1 times the ln of 4. And of course, ln of 4 is still just a scalar, just a constant, it's just a number. So let's differentiate. We're going to get 1 over y times y prime. Over here, we're still going to have the derivative of square root of x plus 1. That's still going to be 1 over 2 square root of x plus 1. And then we're still going to multiply by that scalar ln of 4. So this whole guy will be multiplied by y. So we're going to get that y prime is equal to the natural log of 4 divided by 2 square root of x plus 1, all times y. But what is y prime? Oh yeah. Or sorry, what is y? Y is equal to 4 to the x, square root of x plus 1 power. So here we go. We got the exact same derivative that we had on the left side. Okay, so we're gonna see if I'm psychic here for a second before we finish off this problem. So I want you to think for a second. We've done the inverse ops method and we've used the log differentiation method. I want you to think about, if your life depended on it, which of these methods would you use right now? Like if someone walked in, like alien race came in to this room and said, "Puny earthlings, you are to differentiate y equals 4 to the square root of x plus 1. Do it now or I vanquish your species." Which one would you use? Okay, so go ahead. I want you to first raise your hand if you would choose the inverse ops method. Okay, so if this is first period, I'm going to predict 0 of you guys say this. If it's sixth period, I'm going to predict Colby raised both hands. Okay, put your hands down. Oh wait, there's only Colby's hands up, potentially. Okay, so now how many of you would choose log differentiation? Yeah, that's what I thought. Like, this is the method that everyone seems to really like. So unless you're a memorizer, in which case, go your own way, do your stuff, most of you are probably going to want to find the derivative using this method. Log differentiation is really powerful for doing this. So go for it. Either way, once we've got it there, so score. Let's look at the score here really quickly before we leave this be. So score, I would say it's approximately infinity to approximately 1. So, or, in sixth period, Colby, both hands might count. So with that said, what was our purpose here? Back in the day, we were trying to find the slope of this tangent line. Now, why would we want to do that? Well, that's a different question. Like, forget that. Set that aside for a moment. What we want to do is we want to find the slope here. So what we need to do is we need to, in both cases, or in either case, they're the same thing, so we can go either way. We need to plug in x equals 3 and see what we get. So let's do that right now. I'm going to do it on the right side because I don't want to repeat it both times. So ln of 4 over 2 square root of 3 plus 1 is 4 times 4 to the square root of 4 power. So of course I'm being really careful here. You probably could do this a little faster. I have ln of 4. 2 times square root of 2 or 4 is 4. 4 to the second power is 16. That's going to be equal to 4 ln of 4. So that says that the slope of the tangent line in this case is 4 ln of 4, which you could also write, if you wanted to, as ln of 4 to the 4th power, which is the ln of 256. Both of them work pretty fine. So this is our final answer. Yeah, just keep laughing at my box. If you think I can't hear you, I can hear you all the way from the small gym right now. So there is our slope. So lovely. So now, of course, we can check on the calculator, like, does this turn out to be correct? And we will, just because that's what I got to do. I can't do anything else with you guys. Can't pull up a picture of a weird-looking dog or anything. So first thing is, let's do 4 ln of 4, just to see what that value is, because this is supposedly what the slope is, 5.545. Let's graph that function and see what the slope is. 4 to the power, square root of x plus 1. So we're going to graph this puppy. That's not going to work because I picked a bad window. Let's go zoom standard. So it looks pretty steep there. Pretty steep. Let's look at second calc. Let's do dy dx. Let's figure out what the slope is at x equals 3. 5.5451. 5.5451. Winner! Looks like we got it. What have you won? Well, you finished a math problem. Yay us. But there we go. Basically, it doesn't matter to me which method you use, but I think you're probably going to choose this method, like my class did last year, but of course I didn't learn my lesson. So there we go. We've seen it a little bit. Like, this would be as bad a problem as you could possibly get on any sort of assessment, and it's way worse than anything the AP test would feature involving something like this. Like in past years, the worst I've seen is 2 to the x. So take that for what it is. Okay, so what's left? Couple problems for you to try. That's it. Alrighty, so those try-its. Let's do them right about now. The only thing I'm going to do is I'm going to fix one little mistake I have on here, which caused a whole lot of issues in the last one. So, of course, what I want you to do is I'd like you to write down these problems. They're labeled as A and B. Try-its A and B for the day. I'd like you to pause the video in just a second, give everyone a few minutes to work on it. So Ms. Cooper or Mr. Shibata, of course, thank you again for doing what you're doing today. But pause the video for a little bit, let them work, let them talk about it. Let's all look at these problems, try to see if we can work our way through them. And then, of course, afterwards, just unpause it, and I'll finish up explaining these guys a little bit quicker than I would normally go through them. So go ahead and pause the video now, or maybe even now. Did you pause again? Okay, I'm going to assume that you paused it. So we're back. Let's take a look at these two guys. Let's get the answer for each of these guys up here first, just in case everyone's already got the answer down. So for the first guy, my answer turns out to be 10e to the sine of x times 1 plus x cosine of x. My answer for the second guy, now that I have it written correctly, is y minus 9 equals 108 ln of 3 times x minus 2. So there are my two answers. I'm going to go through each of them right here, but of course if everyone in the class already has it all perfectly down 100%, you're all awesome, you can stop the video right now. Or if you're doing it at home, of course you can stop whenever you want. Thanks for watching. So what do we got here? First one, let's start with this guy. The key thing that I recognized is I saw a product rule. I saw 10x times e to some power, so that means I'm going to use the product rule and break it up with 10x and e to the sine x as my two functions. So as I go through and look at g prime, my first piece is to figure out the derivative of 10x. That's just equal to 10. And then e to the sine x comes along for the ride. On the second one, I'll keep the 10x. But now I've got to do the derivative of e to the sine x. But I know from doing the chain rule a whole bunch of times, it's e to the f times f prime. Derivative of sine is cosine. So from here, all that's left is the simplifying to pull out all the GCFs that are there. I see a 10 in both pieces. I see an e to the sine x in both pieces. All I'm left with is a lonely 1, and then an x cosine of x on the second half. So there is that same answer I wrote off to the right side. There is our problem. I think it's a pretty good low-level, mid-level problem that shows me whether you understand how to use the product rule as well as differentiate an exponential function of base e. So cool, lovely. Okay, the second guy. We've got a tangent line part just to kind of keep you in the game with tangent lines. It's always a nice easy application to ask you. But of course what we want to do is we're going to need to eventually take the derivative of y equals 3 to the x cubed minus 6 power. Not a pretty sight. We can do it. I know we can do it. So first, before I do anything else, I don't know what the y value is at this point, and I know I'm going to need it in the tangent line equation. So I'm just going to plug in 2 over here. So 2 cubed is 8. 8 minus 6 is 2. 3 to the second power is equal to 3 squared, otherwise known as 9. So I've got to find the tangent line at 2, 9. So I've got that piece and that piece from what you see in the answer down here. So next thing, of course, is finding the derivative y prime. And what I'm going to do is I'm going to use log differentiation, because I figure all of you probably want to do that. So I've got ln of y is going to be equal to the ln of 3 to the x cubed minus 6. I can, of course, bring down my power now. Bringing down the power. That's not actually a real song, but, you know, it's okay. So there's my stuff. Now I want to differentiate it. Take my derivative. I've got 1 over y times y prime. On this side, it looks like, oh, product rule, ooh, but we don't need a product rule. ln of 3 is just a constant. In fact, it's about 1.1 something, I think, if memory serves. So, in fact, the derivative over here is really just comes down to what's the derivative of x cubed minus 6. That derivative is 3x squared times the natural log of 3, which is just a scalar. So now, of course, we want to find y prime. So that's going to be 3x squared ln of 3 times y. But what's y equal to? Oh yeah, it says it right here. So y is equal to 3 to the x cubed minus 6. So wonderful little thing. We just got that to work out. Change the purples a little bit. So there's our thing. Of course, the reason we want to do that is we want to be able to plug in x equals 2, because that's going to give us our value of the derivative at x equals 2, which is also known as the slope of the equation there. And we need the slope for the point slope form. So from here I just need to plug in everything in order to make this work. So m is going to be equal to, we're plugging in 2, so 3 times 2 squared is going to be 12, ln of 3. And then over here, we talked about it earlier, we found that 9 earlier, 3 to the 2 cubed minus 6 is 3 to the 8 minus 6, which is 3 squared, which is equal to 9. So this whole thing is going to be equal to 108 natural log of 3, which is my slope, which shows up, voila, right in there. There's my slope. So yeah, it's not pretty. And yeah, there are other ways you could have written it. You could have pulled out 4 or something and written the slope kind of differently. But in fact, I think that's the cleanest way to go. And there is the equation of the tangent line, 2y equals 3 to the x cubed minus 6. So probably the level of question that you would be asked on any sort of assessment. Okay, so with that said, are there any questions? Still can't answer them. Hope I didn't fool you. So with that said, I'm exhausted, I'm tired, and I'm not even here. Like, I'm really speaking to you from the past. Like, this is really Tuesday for me. But anyway, I've gone through the couple examples for you. So just to kind of reiterate what we've done today, we came up with this new rule. We just kind of proved it and derived it using some log differentiation. We found out the derivative of e to the x is e to the x. We went through how that it works with the chain rule, and we used it to find some extrema, noticing that e to the x is always positive. We then used that same idea, like the similar ideas, to work through and figure out what the derivative of any base power to the x was equal to. Found out it was ln of b times b to the x, as long as b was, of course, positive. We had a couple different ways to do it. Probably pretty much every one of you voted to use log differentiation to find the derivative. Totally cool. Stick with it. It's a good way to go. And then finally gave you a couple problems to try that asked you to use some product rule with some e as well as some tangent line stuff to go through. So with that said, if you have any problems, the video is on YouTube. You're welcome to watch it and go watch it and see what's happening there. Otherwise, of course, I'll be back tomorrow. The homework's up. The solutions are up in the course locker, so you'll be able to see that. And either way, I hope you guys have a great day. I hope this was a valuable use of time. And this is Mr. Steele signing off. Have a good morning/afternoon, depending on which time you are.